Hello everybody, welcome to your first online lesson. We're going to be starting off the second part of the trig with understanding the unit circle. So, whether you've seen it before or not, let's get straight into the unit circle. It is a circle with centre at 0, 0 and radius of 1 unit. But we define it around the centre so we can do lots of interesting math with it, mostly to do with trigonometry. So first of all, let's think about this circle and let's in particular consider a point P anywhere on the circle. Well, if you think about the point P, you could construct a right angle triangle where the angle inside that triangle, defined as theta, could help us with some right angle trigonometry to find the opposite and the adjacent. As well as being a right angle triangle as well, that means that Pythagoras holds. So if we think about Pythagoras in this context, well, the opposite is a bit like the y coordinate and the adjacent of that angle is a bit like the x coordinate. So if we define them like that, then we can say that x squared plus y squared is equal to the radius squared. And in this case, we have radius of 1. We can say that x squared plus y squared is equal to 1. Carrying on from there, there are other things we can think about as well. Well, as I mentioned, we are defining a point and we're thinking about a particular angle known as theta. And in the previous example, our point was maybe there and theta is here. Well, we can extend theta. That P could have been here or here or here. And in this case, it's here, look. And that theta can extend right round the circle. And if we're in radians, that means right round the circle is going to be 2 pi radians or 360 degrees. And just as a default, we go in the positive x direction this way. So if we're looking at angles, that's the way to rotate, okay? So this gives us some nice results. If we rotate 210 degrees, say, around there, it would be the same as rotating in the negative direction 150 degrees, going around there. Now, let's get more into the trigonometry now. So we have that point P, and we've defined it as such. We've got our two sides. In this case, we called them A and B. And as you can see, the y coordinate is the height of that triangle. So in the context of the angle theta, it's the opposite. The x coordinate is A, so that would be the adjacent. So if we think of that, we can think about some right angle trigonometry, because we know that the cosine of any angle is the adjacent over the hypotenuse. So in our triangle, the adjacent is A, the hypotenuse is 1, so the cosine of that angle is A. The sine of the angle, well, that's going to be the opposite over hypotenuse. And of course, the opposite is B, hypotenuse is 1, so B over 1 is going to be B. This basically helps us to come up with the fact that this point P could be defined not in terms of A and B, but in terms of theta. Because if we think of the point having an x coordinate of A, well, we've just seen that that x coordinate of A is the same thing as the cosine of the angle. The point, the y coordinate being B, is of course the sine of the angle. So therefore we can swap that in here. So we could define that point to be, rather than AB, cosine theta, sine theta. Now, very quickly, let's have a quick note on tan. Tan is going to be the opposite over the adjacent. So in this case, that means we've got B over A. And as we've seen, we've just worked out that B, here it is sine theta, and A is cosine theta. So our tan theta is going to be that B over A, which is sine theta over cosine theta. This is an important result. Please make a note. Tan theta equals sine theta over cosine theta. We will be using that identity quite a bit over the coming lessons. Now, even further. So just to make sure we're clear about this, the cosine of the angle is the x coordinate of the point, and the sine of the angle is the y coordinate of the point. So we could even think of the axis, the x-axis, a bit like, rather than an x-axis, as the cosine theta axis, right? Or a way of finding wherever cosine theta is. If the point here, P, has a particular value of theta, then its x-coordinate is the cosine of the angle. If we can therefore think of the y-coordinate as being a bit like, or the y-axis, a bit like the sine theta axis. That point P has a particular y-coordinate of sine theta. That is going to be the axis we read it off. So, in summary, some things we can certainly say. Well, from Pythagoras, we worked out earlier that x squared plus y squared was equal to 1. And we now know that the x-coordinate is cosine theta and the y-coordinate is sine theta. So therefore, we can replace them in that Pythagoras and come up with this result, the Pythagorean identity. Cosine squared theta plus sine squared theta is equal to 1. Now, just to be aware as well, in terms of notation, when I write down cosine squared theta, what I'm really talking about is the same thing as saying cosine theta squared. It's just notation that we write it in this particular way. Other things, well, on the unit circle, we know that we have x coordinates ranging from -1 to 1 and y coordinates ranging from -1 to 1. So therefore, it means that obviously, if we're replacing x with cosine theta itself oscillates between -1 and 1, as does sine theta for exactly the same reason. And as previously discussed, tan theta is sine theta over cosine theta. Now, other things that are important about the unit circle, we could extend this past 360 degrees, or if we're in radians, past 2 pi. We can revolve that angle round. There we go. That would be an angle of 2 pi, but we could revolve it again to 3 pi, 4 pi, and so on and so on and so on. And in fact, if we have an angle here of theta, well, if I added 2 pi to that, it's going to be exactly the same. So cosine theta is the same thing as cosine of the same thing plus some multiple of 2 pi. It could be many revolutions, and it's exactly the same principle for sine theta as well. It just keeps revolving and revolving and revolving. Now, if we think about sine theta over cosine theta being tan theta, well, this particular value here of sine theta divided by cosine theta is going to be exactly the same as this one, because the negatives are going to cancel out. So this is telling us that, well, tan theta is not going to oscillate every 2 pi like cosine and sine. It's going to oscillate every pi. We say the period of the graph of tan theta is pi radians, while the period of the graph of cosine and sine theta is 2 pi radians. Now, other things that are really important. We wrote these down earlier on, but this is the special triangle that we need to be aware of. This kind of needs to be committed to memory. Now, of course, if we know this already, and this works through Pythagoras, we can have any sort of factor of this triangle also making sense. And what I want to do is actually swap it out for one half the size. So let's keep the angles the same, but perhaps rather than writing 45 degrees, we should probably write pi over 4 at this point and be in radians. Well, I want to have this as 1. So what this means is I'm going to be dividing every side on the original triangle by √2. That's going to generate that 1 for me, which will mean this is 1 over √2, and this is also 1 over √2. Now, this is a better version to remember of the special triangle than the one originally given, because think about this as an angle moving around the center point. We now have a radius of 1, just like the unit circle. So this is going to come in quite handy to remember. And we can therefore map it onto the unit circle, because if we have an angle of pi over 4, well, okay, that means we have a hypotenuse of 1, and it means these lengths are 1 over √2 and 1 over √2. So this coordinate point is 1 over root 2, 1 over root 2. And due to the symmetries of the graph, we can find all of these other coordinate points that are really important for particular angles. The other special triangle we can approach in exactly the same way. So this is the triangle that you wrote down and know. Well, I want to use it in a context that is useful for the unit circle. So rather than having a hypotenuse of 2, just like last time, I want to have a hypotenuse of 1, which means I can keep this the same. And let's convert again into radians. But if I have a hypotenuse of 2 on the original, if I divide every side by 2, I'm going to get this hypotenuse of 1 that I want. So that means that root 3 is going to become root 3 over 2, and 1 is going to become a half. So it's very useful to memorize these particular numbers and angles so that we can apply them to the unit circle. So remember, we've got root 3 over 2 and a half. So this, it's a little tricky to follow this, but consider perhaps this triangle here. Well, you can see this is the smaller of the two angles. This is going to be the pi over 6, which means that that height there is a half and the longer length is root 3 over 2. That is literally being swapped out from these numbers here. So if I know that, you can see why this coordinate point has an x coordinate of root 3 over 2 and a y coordinate of a half. And if we think about this particular version of the triangle, well, this angle is pi over 3 now. And again, you can see the smaller length is a half, the longer length is root 3 over 2. That is where this coordinate point is generated from. And all of the others are coming from the symmetrical properties of the graph. Of course, if we're past the 0 point of the x-axis, then we're going to have a negative x coordinate right here and here. We can work out all of these properties quite, I wouldn't say easily, but with a little bit of effort. In the next video, you're going to see some examples of the sorts of questions you'll need to answer and how these properties can be used.